Yeah. All right. So our last speaker of the session is Marco Campion, who's going to tell us about a formal framework to measure the incompleteness of abstract interpretations. So take it away.
Okay. Thank you for the introduction. This is a joint work with Caterina from INRIA, Mila Dalla Preda from University of Verona, and Roberto Giacobazzi from University of Arizona. So in this talk, I'm going to formalize the minimum requirements that a distance function should meet in order to measure the incompleteness of abstract interpretation. So again, we are speaking about completeness, and its weakening. It is the partial completeness in this case. So just a bit of background before. What is the key idea of abstract interpretation? In this case, the key idea is to provide an approximation, so replace the computation of concrete operators over undecidable properties by abstract operators over approximated decidable properties. For our purposes, we are just requiring a very small structure between the concrete properties and the abstract properties. So we require at least an ordering, which is a pre-order, and a concretization function from the abstract properties to the concrete properties. So it might also not enjoy the Galois connection. So when an abstract operator is sound, then an abstract operator is sound when is a sound approximation of a concrete operator when the concretization of the result of the abstract operator is always an approximation of the result of the concrete operator over all possible abstract inputs. So the best possible scenario is when this inequality becomes an equality. And in this case, we get the so-called forward completeness, so the completeness over the concrete properties. Namely, the abstract operator is forward complete for all possible abstract inputs. We can require also a weaker version of forward completeness, which is called the local forward completeness, when we require completeness over just an input. So in this case, it might happen that the result is not the same in the concrete properties. So when concretized, when the result of the abstract operator is concretized over the concrete properties. So in this case, we have a forward incompleteness. When the concrete properties and abstract properties enjoy a Galois connection, so through an abstraction function, then in this case, we can formalize the well-known backward completeness properties, which is the property that was in the previous talks. And this property says that an abstract operator is backward complete for respect to a concrete operator for all possible concrete inputs, in this case, when the result of the abstract operator is the same as the result of the abstraction of the result of the concrete operator, in this case. And also, again, we have the local version. So we say that is local backward complete for a concrete input when the equality holds for that input. So it might happen that it is backward incomplete for a concrete input. It has been proved that this property, when used to prove program property, when used to verify program properties, is very hard to achieve or even impossible, also for the local version, for the backward completeness. So that's why in the POPL 2022, it has been introduced the partial backward completeness, which is a weakening of the backward completeness property, namely of the local backward completeness property, because we are requiring, so we allow incompleteness over the result of the abstract operator and the concretization of the concrete operator, but we require that this difference is limited to an epsilon amount, which is measured by a quasi-metric distance. And these are the axioms that define the quasi-metric in this case that we will see better later. So for example, as a quasi-metric distance, which measure in this case, the incompleteness over the interval abstract domain, we can define the weighted path length that sees the interval abstract domain as a graph, as a directed graph in this case, as a weighted directed graph, where we have the weight over each edge. And in this case, the distance is simply the minimum weighting path between two comparable elements. So for example, the distance between the interval 0, 0 and the interval -1, 2 is 3, meaning that there are 3 more discrete elements between these two intervals. It is undefined for non-comparable elements. And it is infinite if, of course, there are infinite more elements between two comparable intervals. So note that in this case, the quasi-metric here defined, the weighted path length, satisfies this if and only if. Namely, whenever the distance returns 0, then we are sure that the two elements that we are comparing are equal. So now we are, I want to show you why it is limiting to use quasi-metric to measure incompleteness. Well, let's start by analyzing the axioms of the quasi-metric. So the first axiom requires that the distance function should return a value only on comparable elements, but in this case is not really necessary, because we can even allow the distance to return any value on all elements, even on uncomparable ones, because actually we are using this distance function to measure the distance between two comparable elements, because we are measuring the distance between the result of the concrete and the abstract analysis, which by assumption is sound. So they are always on the same chain. And the second axiom in this case is really too strong, because here this axiom is requiring the distance function to adhere precisely the underlying ordering, namely to return 0 every time we are measuring the distance of the same element. But in this case, the left implication is too strong, because maybe we are interested in formalizing a distance which is an approximation, which is approximating the computation of the distance between two elements. So in this case, the distance maybe even return 0 on two elements that are equal, because the distance itself is seeing the two elements that are in fact equal. So for example, suppose that we want to define a distance on the concrete properties in this case, and we don't have a Galois connection, for example, on convex polyhedra. And in this case, we are forced to define a distance that recognizes when two elements are equal. So it must study all the information inside the concrete elements. So we are not allowed to define distance which approximate the computation. And also the last axiom, which is the triangle inequality over chains, is not really necessary. So we are now formalizing a new distance function, which require just an ordering over our set of properties, which it is at least a preorder. So this is the signature of our new distance function, which always return, in sense it is a metric, it must be a matrix, so it always return a value. And this is the only requirement about the metric that we require, so only the right implication. When the two elements are equal, then the distance must be 0. But it might not be the case with the left implication. And in the literature, these two axioms define what is called a pre-metric in this case. So we need a sort of compatible axiom over the ordering. So what we are requiring for the distance function is that when we are measuring the distance between elements of the same chain, then we require that the distance between, say, x and z is always greater or equal than the distance between any elements in the middle. So this is the only requirement that we ask for respecting the ordering in this case. So when a distance function satisfies these two axioms, then we say that this is a pre-metric compatible with the pre-order relation of our domain. For example, the weighted path length that we have defined before is a pre-metric compatible on the interval abstraction. But we can even define another pre-metric here. Suppose that our elements is a vector of intervals, and we can define in this case a metric that is interested in measure just the distance between only one component of that vector, for example, the I component. So in this case, we are using the weighted path length for measuring that single component. And this is a pre-metric compatible with this domain. And note that this is not a quasi-metric, because the distance in this case is measuring just the distance between two single intervals and not all the vector. So it might be the case that the distance is 0, but the two vectors are not the same. So as another example, suppose that we want to define a distance over the convex polyhedra domain. So in this case, we can define, for example, the distance between two polyhedra as the absolute value of the difference between their volume, where vol in this case is a volume function that calculates the volume. This is a pre-metric compatible with the convex polyhedra domain. And here, thanks to the few axioms that require the pre-metric, we can even over-approximate the real volume here with this metric. So this may not be a quasi-metric. So now we can use the structure of pre-metrics to derive also pre-metrics from between domains. So suppose that we have the concrete properties and abstract properties are just they share a concretization function. We don't have a oops, sorry. Let's stop the presentation. Okay. So we don't have a Galois connection in the left case, but we have defined a distance on the concrete properties. Well, in this case, we can derive another distance on the abstract property by using the concretization function, and this distance is still a pre-metric compatible. Of course, it's measuring something which is approximate. So, for example, we can reuse the same metric from polyhedra to calculate the volume of other representable abstraction like octagons or intervals. We can do the same also when we enjoy there is a Galois connection between two domains. So we can, from a distance defined on the abstract properties, we can derive the distance on the concrete properties by using the abstraction function, and this is still a pre-metric. So we can now define a revised version of our partial completeness properties. So the partial backward completeness properties now uses this definition of pre-metric. But we can also now define the epsilon partial forward completeness properties, because we can now define also distances of the concrete properties. So we can say that the abstract operator is epsilon partial forward complete when the distance between the result on the concrete properties, between the abstract and the concrete operators is at maximum epsilon. And here, again, we are using the pre-metric compatible over the concrete properties. So as a last very simple example, we just show how we want to verify the epsilon partial forward completeness on this small program. So here we are using the interproc static analyzer to infer the looping variant of this program. And we are using the abstract domain of octagons and polyhedra. We want to measure the incompleteness in this case using these pre-metrics. So what is the calculation of this metric, of this pre-metric? Well, we are calculating the more volume that has the result of the abstract interpreter with respect to the result of the concrete interpreter. So this is the percentage of more volume that has the result of the interproc static analysis with respect to the concrete analysis, just as an example. So we are asking whether the result of interproc using polyhedra and octagons is 20 partial forward complete. Namely, whether the imprecision injected by interproc, the percentage of imprecision injected is no more than 20%. And this pre-metric actually is computing the volume using an approximation because we are calculating actually the volume of rectangles. So we are applying another level of approximation. We are considering the result we are approximating the result as rectangles, so we are calculating the volume of rectangles. So the computation is much faster in this case, without computing the exact volumes on polyhedra. So for example, these are the results. These are the invariants generated by interproc, with the octagons on the left and polyhedra on the right. These are what the pre-metric is computing. So it is taking their approximation over rectangles, so over intervals, actually, over boxes. And this is the result between those two. So it actually says that the result of the octagons analysis has approximated 33% more volume than the result of the polyhedra analysis in this case. And similarly, the result between the polyhedra analysis and the concrete analysis is 20%, as an inaccuracy of 20%, while between the octagons and the concrete analysis is 60% more. So we can conclude that the analysis of interproc over polyhedra satisfies our properties, which is the 20 partial formal completeness for all inputs in this case. But the octagons analysis does not satisfy this property because it has more inaccuracy in this case. Just an observation here, we can also characterize the local forward and backward completeness when our pre-metric that we have defined satisfies this action, namely it can recognize the equal elements only on comparable elements. Then we say that in this case the pre-metric is strong. So for example, the weighted palen, which is also a quasi-metric, of course is strong, while the metric with the pre-metric that we had defined before is not strong because it approximates the result by computing the volume of rectangles. So it may calculate the distance 0 even if the two elements are not the same. So in this case, we have two theorems. So if we had defined a distance over the concrete properties, which is actually strong, then if we are able to prove that our abstract operator is 0 partial forward complete over an input, then we can say that is also locally forward complete, and vice versa. And if we have defined also a distance over the if we have defined a distance over the abstract property and this distance is strong in this case, then we can say that if we are able to prove the 0 partial backward completeness over an input, then we are sure that we are also locally backward complete and vice versa. So why it matters? So why it is important to study this kind of metric? Well, this is because we must be sure that what we are using to measure the incompleteness, so the imprecision of our analysis, must satisfy at least a few axioms to be used to have a meaning in this case. So we should define a distance that it is measuring what we are interested in order to control, for example, the incompleteness propagation, maybe because we have to check how we have designed the abstract interpreter. And also, thanks to the very few axioms that require the pre-matrix, we can derive and combine pre-matrix, derive from other domains and combine pre-matrix that we have already defined. And this could be also a way to measure, for example, the potency of code obfuscation techniques when used to obfuscate the analysis, to worsen the analysis in the case. And that's it. Thank you.
We have time for questions. Quite a bit of time. Don't be shy. All right, I'll ask one to kick it off. So I guess you gave some good intuitions for this measurement when you're in terms of volume for numerical abstract domains, and I kind of see that. I have no idea what that would look like for something symbolic, like separation logic domains or something like this. So I don't know if you have any thoughts.
So I didn't understand the question.
So all your definitions in these metrics make sense from a numerical domain context, yes. Right? In terms of measuring volume and the differences between octagons.
Yes. Okay. So actually, we have defined the examples that we have provided in the paper are most of them numerical actually. We have also an example over like a very simple concrete domain, like the set of traces in this case. But our idea was actually to just give the axioms on what we have to satisfy in order to define any kind of distance that measure the incompleteness over any domain of properties in this case. So even non-numerical properties.
Okay. Can you give a little bit of intuition of that for non-numerical ones?
Okay. For example, over if we are considering, like for example, I don't know, the set of traces, for example, we can define just as a measure between the result of the abstract analysis and the concrete analysis, for example, just to measure how many more spurious traces that we have between these two results. And this is still a pre-metric in this case.
Mm-hmm. Okay, thanks. Yeah. All right.
So how do you calculate the distances manually using pen and pencil or automatically?
Well, in our paper, we just did it manually. So we didn't implement it any distance. We did just a theoretical formalization in this case. So, but the idea is that usually when someone is designing an analysis, a static analyzer, at some point he must like it must be controlled the incompleteness in this case. So at some point you have to define an evaluation. So how many, for example, false alarm your analysis has generated. So in a sense, you are defining a pre-metric in this case.
Other questions? Check online. Yep. All right. Okay. Can we close the session then? All right. Thank you.